So thanks, Andy. Thanks for the invite to talk here. And you're going to hear things like this at least 3 times because you've already heard them from Andy about the Cartan connection. That was last week. And then here and also on Monday, I'm going to be talking about things related to the Cartan connection. And then actually the following week, you're going to hear them all over again from Rod Gover. Right, but of course, you may not even recognize that they're the same subject to start with. So, because we'll all be coming at it from different angles. Anyway, here we go. So this is about the ambient metric. And if you can see me as well, I'm now holding up the ambient metric. This is a book which was published a few years ago now by Charlie Fefferman and Bergman-Kernel. And that's the main topic. This book is the main topic of this talk. Right, so, yes, okay. So my talk is going to be, I'm going to mention some articles that I like this one. This is by Roger Penrose from 1959. And I'm going to tell you, roughly speaking, what's in each of these articles, or some snippet thereof, and they're all connected together somehow. So this one here, the apparent shape of a relativistically moving sphere is just concerned with space-time, or Minkowski space. And actually, I remember reading as a school child some expositions of special relativity where people were saying you could look round corners and things like that, which is of course complete nonsense. You see the same view no matter how fast you're moving. It's just that your viewpoint thereof changes, and it's exactly like this. So here is space and time. Except I've suppressed one of the space dimensions, of course, in order to fit it on the screen. And here is space-time with its normal Lorentzian metric and null cone. So these are the light rays going along the generators of this null cone, emitting from the vertex of this null cone, which is an event in space-time. And this thing here, because I've suppressed one of the dimensions, is actually the celestial sphere. So it looks like a circle, but it's not. It's a sphere, of course. And the point is that the Lorentz group is acting on all this. So the Lorentz group is the group of isometries of space-time which are preserving this event. And in particular, it acts on the sphere, of course. And how does it act on the sphere? Well, it acts actually conformally on the sphere. So that when you look out at the sky and you see the celestial sphere, if somebody else comes whizzing past you at some speed approaching the speed of light, they will see the same sphere, but they'll see it distorted. But the way it's distorted is by conformal transformations. So the Lorentz group is realized as conformal transformations on the sphere. In particular, a sphere looks like, well, it looks like a disk, and it still looks like a disk no matter how fast you're traveling, because conformal transformations for the sphere preserve disks. Right, so that's an article from 1959 about...
How many?
Sorry? The comment? No, okay, I'll just continue, let's see. So, and now there's hyperbolic space. Yeah, okay, so so now I'm going to draw the sphere as if it's really a sphere. Here it is, that's a sphere. And I'm going to tell you what's in Beltrami's article, which is about the fundamental theory of spaces of constant curvature. And I noticed that actually this is perhaps where the terminology of constant curvature actually comes from. Perhaps, I don't really know. But anyway, here's a sphere. All right. Now, actually, although I've drawn it as a regular, honest, two-dimensional sphere, you can equally well view this as a representation of the n-sphere. Again, I'm suppressing lots of dimensions. And if you want to relate that to the previous diagram, you should think of the sphere sitting inside the space of rays. These are light rays sitting inside all rays. In other words, think of it as sitting inside real projective space of one bigger dimension. And then, of course, acting on this, there is the thing which actually preserves this sphere is the Lorentz group, but in higher dimensions. And I've added this little arrow here, just so that it's the connected component of the Lorentz group. So this thing acts on the sphere by conformal transformations. That's what we learned from the last slide. But it also acts on the interior of the sphere. And it does so by hyperbolic motions. So first of all, there's conformal motions of the sphere. Motions is an old-fashioned word meaning connected component of the identity of the group of symmetries. So these are conformal motions of the sphere. And on the other hand, the interior of the sphere, which you can identify with the hyperboloid of one sheet in the Lorentzian space, that acquires a Riemannian metric, and this is isometries of the Riemannian metrics. There are two things which have the same symmetry group, and I should point out that things are a little bit different when n is greater than or equal to 3, because when n is equal to 2, nevertheless, the symmetry group is still SO31, but generally speaking, when n is greater than or equal to 3, a different thing happens. This was observed by Joseph Neuville in 1850, that the local conformal transformations of the sphere are all restrictions of global transformations. The sphere is very rigid from this point of view, unlike the true sphere. Of course, the hyperbolic motions are, of course, again, locally determined. So, but here we've got the same symmetry group on two different spaces. And you might think that means there's some deeper connection between the conformal geometry of the sphere and the Riemannian geometry of the interior. And this is actually true. So here's an application. The application is through this, what is now called holography. But actually, the following argument goes back to Dirac in 1935. So he's actually looking at the wave equation in de Sitter space, but it will turn out that we change the signature a little bit, doesn't really matter. Here is, I've written down the Lorentzian metric. Now I've chosen slightly peculiar coordinates, but nevertheless, this is like, so in a block matrix, this would have an identity matrix in the middle block. In the top right-hand corner, it would have 1. In the bottom left-hand corner, it would have 1. So a symmetric matrix of indefinite signature. Okay, so you look at this thing. This is the Lorentzian metric in Rn+2. And this is the thing that's being preserved by the, by SOn+1,1. So let's give this metric a name. We'll call it R. And also, you can introduce the inverse metric. You can tell because this new metric has upstairs indices rather than downstairs indices, acting on this, this space by means of what would be the Laplacian, except it's got a funny signature. So it's a wave operator. And I'll introduce the terminology ambient here to mean things which are happening in this bigger space. So other terminologies might be or at least projectively, it's the bulk. Okay, but anyway, it's got this wave operator, which is acting in a space of dimension n+2. And you can do the following. This is what Dirac did. So Dirac looks at homogeneous functions. Actually, I've got them to be positively homogeneous here. So lambda is greater than 0. So these are functions which behave in a certain way along the rays emanating from the origin. They scale by a lambda to the power w. Okay, so it's ordinary everyday concept of homogeneous function. And of course, you can think of this as having something to do with functions on the sphere. It's just they've just been, you can get a one-to-one correspondence just by extending them off homogeneously in this way. So anyway, if you do that, and you have to ignore the dogs barking. I just have to tell them to shut up. Hey, shh. Right, they're barking at the. Yes, we have some kookaburras come to visit. Anyway, right. So if you look at this homogeneous function, and if you've got such a thing just defined on the on where r is equal to 0, in other words, on the light cone, you can extend it off the light cone. And when I do that, I'm going to call that f tilde. Okay, but you can maintain that it's still homogeneous. It's just been defined near the light cone, whereas previously it was defined only on the light cone. Okay, and then you ask about the freedom in extending such a thing. Molly, shh. Okay, here's the freedom in extending such a thing. You could replace f tilde by something which is r times something else, because of course on r equals 0, you don't see this addition. So if you did that, G would be homogeneous of degree 2 less than f tilde. So it would be homogeneous of degree w minus 2. And then there's a fabulous calculation you can do. Here it is. So you look at the this ambient wave operator, and you apply it to this freedom. So you apply it to r times G. And you find, rather amazingly, well, I mean, this is a trivial calculation, but it's a really great conclusion, namely that r comes out the front like that, and then you get a factor, a numerical factor, depending on the dimension and the homogeneity. So n is the dimension here, and w is the homogeneity. You find you get a factor times G coming out. And in particular, you notice that that factor vanishes precisely of a particular homogeneity in a particular dimension. So it vanishes if w is equal to 1 minus n over 2. So for example, if w is 0, you're talking about ordinary functions homogeneous of degree 0, in dimension n is equal to 2, w vanishes. Anyway, but this happens in any dimension. This factor vanishes if w is equal to 1 minus n over 2. And therefore, if you do the following arrangement, so you start with f, you look at this extension, you take this, ambient wave operator, apply it to f, and then restrict back down to r equals 0, you get something which has a slightly different homogeneity. It's dropped by 2. But the point is, it's well defined. It doesn't depend on this extension. And you ask, what have you done here? Well, out of thin air, you have created something on the sphere, and it's actually the conformal Laplacian. We'll come back to the conformal Laplacian later, but this is in dimension n equals 2. It's just the Laplacian, which is well known to be conformally invariant. And otherwise, it's something acting on functions of appropriate homogeneity, or if you like, functions on the sphere of an appropriate weight. And it's a well-defined and by construction invariant under this group, this big Lorentz group, acting on the sphere. Okay, so this is a very sort of baby instance of constructing something on the boundary, on the sphere, by looking at things ambiently, looking at things either on the interior or just on the interior and exterior together. Okay, so let's see. I'm just going to mention a bunch of papers now, which use this. So this is just in flat space. Okay, so we're not looking at anything more complicated than the previous coordinates with these groups acting, and nothing else. Okay, so the first thing is that, well, this trick that I did on the previous page, it's a good trick, but it just worked for the Laplacian. Okay, the Laplacian is linear, but of course there are many other well-known conformally invariant differential operators, even in dimension 4. So for example, the Dirac operator or Maxwell operator, things like that. And so you could try and look at fields which were not just scalar fields, but but which were, for example, spinor fields or tensor fields. And you can do that, and you come up with this is quite a detailed article, quite a detailed and long article which does this. And it's called CP5 calculus because rather than RP5, they've complexified everything to make it CP5. And the reason that they've done that is because this is motivated by twistor theory. So, of course, twistor theory is another theory which uses coincidences among low-dimensional Lie groups. And in particular, for example, the various coincidences between things like the Lorentz groups being isomorphic to various other groups like quaternionic groups and things like that in dimension 4. And in particular, one of the things you can do is write down what spinors look like in dimension 4 using some more global and coincidence of Lie groups. So anyway, this is based on twistor theory. Okay, so here's another article which is just using, and this is just using, I emphasize, just using this flat holographic principle. So the previous slide, we were looking at the Laplacian acting on conformal densities of a particular weight. In this article, we're asking about nonlinear differential operators rather than linear differential operators. So, for example, things like the Schwarzian in projective differential geometry have a conformal version, and it's not so obvious how you even write down invariants of conformal densities at all. Never mind show that this is all you've got. I just mentioned that this ties in with a lecture earlier by Ian Anderson on the variational bicomplex, and we actually use, so in this article with Robin Graham, we use the variational complex, that's the thing that runs along the bottom and up the right-hand side of the variational bicomplex, in order to prove at some stage that we've found all of the conformally invariant operators acting on functions. Okay, then you can ask about nonlinear things acting on tensors. Right? So this is an article a little bit later, which is, again, it's using the flat theory, but it's trying to work out what all of the invariant gadgets you can construct in conformal and CR geometry by using this trickery, this holographic trickery, but applied to tensors. And I should mention that there's a very close relationship between conformal differential geometry and CR differential geometry. So CR geometry is the geometry that you get on the boundary of a ball in complex space rather than in real space. But some of the tricks are very, very similar. And in fact, this article by Toby Bailey and Robin Graham and myself is answering some questions which arise in, well, first arose in CR geometry, and we will get to that soon. Okay, then of course a little bit later, 1998, there's a couple of articles where, for example, Ed Witten introduces the terminology of holography, which I've just been now using. Okay, and then a little bit later, here's an article about, again, using the flat holographic principle to try and investigate, well, what are these? These are differential operators that preserve harmonic functions. Okay, so surprisingly, that's a tricky problem to work out which linear differential operators, even on Rn, preserve harmonic functions. So this was a question asked by Ed Witten and answered in this article. Right, but now we come to the ambient metric, which is the main topic of this talk. Okay, so here's some history. Again, all of the things in orange boxes are key articles. And the first article has nothing to do with, apparently has nothing to do with conformal geometry at all, or indeed, well, anything other than actual complex analysis. So, but nevertheless, this is a landmark article, and it concerns, well, biholomorphic mappings between pseudo-convex domains. Okay, so a pseudo-convex domain, well, a domain is just an open subset in Cn for, n, well, generally speaking, greater than 1. Otherwise, everything is answered by the Riemann mapping theorem. Otherwise, if you're in n greater than 1, so in several complex variables, then you can ask about domains in such spaces and ask if they are biholomorphically equivalent. And the really remarkable thing which is proved in this article is that in the pseudo-convex case, which means basically the boundary is convex under an appropriate holomorphic change of coordinates, in the pseudo-convex case, there's this gadget called the Bergman kernel, which gives rise to a metric. That metric, if you look at it in the round ball, is actually just the holomorphic version of the hyperbolic space metric in real geometry. But anyway, the point is that you can show by very careful analysis, or at least Fefferman can show by very careful analysis of the geodesics of this Bergman metric, that these biholomorphic mappings actually extend holomorphically, right, as smooth mappings right up to the boundary, and therefore you're in the realm of CR geometry. Okay, so then 2 years later, he asked what happens if you start with the boundary. So you start with the boundary of a pseudo-convex domain and you try and build the interior. Okay, and so this is like you've got the sphere sitting in complex projective space with the appropriate symmetry group, and you're asking about can you build the interior of that sphere just from the geometry of the sphere itself, and you can. Okay, now here is an article where I just want to point out this article because Parabolic is introduced perhaps for the first time in the title. Parabolic invariant theory. It has been noticed already then by Fefferman that the appropriate geometry here is being controlled by a semi-simple Lie group modulo a parabolic subgroup, which featured heavily in Andy's talks at the opening of this conference. And so, it's very key that you're trying to analyze invariant theory for this stabilizer subgroup, this parabolic subgroup. Okay, so you can do it in complex analysis, but you can also do it in conformal analysis. And now, here we come. Right, so 6 years later, so Fefferman and Robin Graham now got together and realized that the construction, which is in the 1976 article of Charlie Fefferman, just goes over to the case of conformal geometry with some differences, with some similarities and some differences. Some bits are harder, some bits are easier, but that was the state of play in 1985. And this article revolutionized the study of conformal geometry and conformal invariants in various ways. Okay, and then they always claim to be writing up a proper version of this. So this, this is a bit sketchy, this 1985 paper. And here we are, 27 years later, at 5 times the page count, there's this little monograph called The Ambient Metric, which I highly recommend. Okay, and this is what I'm now going to be talking about. So these two articles, especially the second article, is what I'm now going to be talking about. So, how does this ambient metric come about? Well, let me tell you a remarkable calculation that indicates that there is something going on. Right? So I'm not going to tell you all of the details of what's in the ambient metric book. I'm just going to tell you some things to get you excited, and then you can go and read the book yourself. Right? So let's look at the flat Lension metric, which was the subject of discussions so far. And all I've done here is change coordinates. So I've written it out in flat space in a particular way so that, well, T is a coordinate running up the generators of the null cone at the origin, and rho is a transverse coordinate. Okay, so all I've done here is taken the Lension metric and change coordinates, and you can easily check that this is the flat Lension metric in suitable coordinates. Okay, and GAB here is, well, in the basic example, it's the flat Euclidean metric in Rn. However, you could try and ask what happens if you allow G to depend actually both on X and on this variable rho, but not on T. Okay, the T dependence in that variable has already been taken account of by this T squared factor in front of the GAB. Okay, that's exactly what you need in order to write down the Lension metric, and with correct dependence on this coordinate running up the generators of the rays. Okay, so here is a potential interesting metric. Its form is based on the flat Lension metric, and all I've done is allow G to be a metric depending on X, and also on this transverse variable rho. Okay, so you should think of this as this metric when you set rho equal to 0 is an initially given metric on a cone. Somehow it's degenerate, but you think of it as initial, and you're asking about what happens if you let it depend on rho now. Okay, and the thing to do, and to model what's happening in the flat case, of course, you cannot ask that this metric be flat without very severely restricting G. But let's ask instead that it be Ricci flat instead, and see what happens. Right? And then you have to do a calculation to see what happens. And this is this remarkable calculation. So let's just do that. And in the book, they say it's a straightforward but tedious calculation. Okay, there are many straightforward but tedious calculations in the book, which I very much like. I like doing straightforward but tedious, in other words, mindless calculations, right? And sometimes they throw up surprising results, and in this case they do. So let's see what happens. So you do your straightforward but tedious calculation, and you find that necessarily this metric as a function of rho has a really nice, easy to interpret tensor at first order. Okay, so what I'm doing here is expanding this as in a power series in rho to see what happens. Okay, so you do that and you find that, lo and behold, you get a tensor, rho AB, at first order, or 2 times rho AB. The reason I've written it as 2 times rho AB is that rho AB is actually a very standard terminology for a well-known tensor in both Riemannian and especially in conformal differential geometry. It's the so-called Shortened Tensor. So rho AB is this following tensor. Okay, so it's an appropriate scale of a trace adjusted part of the Ricci tensor. So RAB here is the Ricci tensor, R is the scalar tensor. So I've first of all taken the Ricci tensor and I've modified it in this way by an appropriate scale, a scalar multiple of its trace. And then I've taken a scale of that 1 over n minus 2. Notice that, I remarked earlier that there was something different between two-dimensional conformal geometry and dimensions higher than 2. And here, this n minus 2 factor, you notice that this doesn't make sense when n is equal to 2. Anyway, this thing's called the Shortened Tensor, and it occurs very, it occurs all over, it's spread all over conformal differential geometry. One of the reasons, the two reasons, one of the reasons is that it transforms in a nice way. So in other words, if you rescale the metric G, you work out how the Ricci tensor transforms by a bit of a mess. Scalar curvature transforms by a bit of a mess. But if you take this particular linear transformation, the row tensor actually transforms by less of a mess. Okay, anyway, but this is the Shortened tensor, and it's the thing which actually, you'll notice it appeared in Andy's talk in an explicit formula for the Cartan connection. So rather than having the Ricci tensor, you have the Shortened tensor instead. Okay, so first of all, this is remarkable, and it throws up the Shortened tensor right off the bat. Okay, and now, of course, you ask about the higher order terms, and then some real magic occurs. So first of all, you could try just adding in a second order term like this. And in fact, just a second order term and nothing else. Just stop at order 2 and put that into this Lension metric and see what happens. Okay, so all I've done here is take the Shortened tensor, take its square as an endomorphism, and taken this for some, completely ridiculous reason, taken this to be the second order terms in an expansion for G, and then just truncated it at second order. Now some real magic happens. If you look at this Lension metric, you find that it is flat if the original metric is conformally flat. Now, I've decorated this with a few smileys because this is very surprising in the fact that, the usual way you would have to deal with a conformally flat metric is, of course, it's characterized in higher dimensions, in dimension 4 and above, by the Weil tensor vanishing. But actually finding a conformal factor to make a conformal metric flat is, pretty much impossible. You can't find the conformal factor, even though it's conformally flat. It's like, it's the Frobenius theorem tells you when things are integrable, but actually finding the leaves or GD6, finding where GD6 go, even though they're determined, is by, it's difficult. So this is difficult, but nevertheless, so you don't need to know this. You just take G, and if it's conformally flat and you plug it into this formula, you get a flat metric. Absolutely amazing. Here is something which is less amazing. So I've just decorated this with a few cups of coffee. If you take your metric instead to be Einstein, and you take it to be, given by this funny formula, relatively simple formula, you find that it's Ricci flat. Okay, so just on the nose, Ricci flat. But this is not a conformal statement. We're trying to use this metric, this ambient metric construction, to study conformal geometry somehow. That's why I'm giving this talk. But this one here, at least it's a pretty nice thing. But more generally, if you look at the second order terms, so we've already got a couple of nice things happening with this particular choice. But if you try and just force Ricci flatness, then again, a mindless calculation, you'll find that this is what happens. So you see the terms that we've got before. So we've got the Shortened tensor at first order, its square at second order. And then you've got another factor. So this factor, which I've called BAB, it's a new tensor, it's symmetric and divergence free. And you notice that the key thing to notice here is that this works if n is not equal to 4. If n is equal to 4, there's just nothing you can put here at second order which forces Ricci flatness in general. Okay, but if n is not equal to 4, you can do it by means of a particular tensor. Now at this point, it's a mindless calculation to figure out what BAB is. here's a formula for it. So it's a derivative. So first is the Laplacian of the Shortened Tensor, then there's the Hessian of its trace. W here is the Weyl curvature.
May I ask something?
Yeah.
The two pink dots, they are just in one direction, or it's an if and only if?
At the moment, just in one direction, just in one direction.
Okay, thank you.
At the moment, yes, we'll come back. Well, I'll mention this again later on. Okay, right, so this thing here is what you have to put there, and you notice that it works if n is not equal to 4. If n is equal to 4, then further magic happens. So if n is equal to 4, then this problem is obstructed. You just can't put anything there. But what you can do is take the formula for B in general for n not equal to 4 and simply set n equal to 4. Okay, this is perhaps a silly thing to do because it's like taking a limit over dimensions or something. But anyway, you do that, you put n equals 4, and you get the Bark tensor in this particular case. And then again, you get a limit, you get a relationship to conformal geometry, because as you probably know, in dimension 4, the Bark tensor is a conformally invariant tensor. Conformally invariant tensors are quite hard to come by, but the Bark tensor is one of them. Now let me try and draw a picture of what's going on. Okay, so that was just a calculation on the previous page. I'm now going to try and draw a picture of what's happening. Okay, so first of all, you're going to start with a conformal manifold. Okay, and the first thing you do is you put a ray bundle over this conformal manifold. I've drawn it like this, there's some sort of hint. This is the bundle of scales. So in other words, as you move up and down these yellow rays here, you are conformally rescaling your metric just at a point. Okay, in other words, a section of this cone bundle is a choice of metric in the conformal class. So you do that, and you can compare this with the formula that I had for this n plus 1 dimensional Lorentzian metric on the previous slide, and you'll find that what you're doing is writing down some sort of degenerate metric on this bundle of scales. But then you introduce this row variable. Okay, so at the moment, if you compare that with the previous slide, this is the t variable. And now I'm going to introduce the row variable into this picture. Okay, and it's a coordinate transverse to this direction. So I've tried to indicate that this has been made one dimension bigger. So the conformal manifold is dimension n, the bundle of scales is dimension n plus 1. This new manifold is now n plus 2. Right, and then you try and insist that this manifold be Ricci flat. And in odd dimensions, if you just go through, this calculation on the previous slide, you're getting into trouble when n is equal to 4. You'll get into trouble when n is equal to 6, but higher up, and so on. But in odd dimensions, no problems whatsoever. You can find a formal expansion. You can find all the terms in the potential in this Ricci flat metric just by induction. Okay, so you do that, and in odd dimensions, you get a complete formal power series to all orders. So in odd dimensions, this is a really good way of relating conformal geometry to Riemannian geometry. With more work, you can even show convergence. You get a real genuine collar on your bundle of scales. In even dimensions, it goes wrong. We've seen it going wrong in dimension 4. It goes wrong in dimension 6, and so on. So this is definitely worrying, but interesting. Okay, so you have to be careful, but then some happiness is restored if you are careful. Now, in order to, and when you do this, everything becomes, you can do it in a conformally invariant way. Okay, so everything on the previous slide was definitely written out in terms of coordinates. Now, this requires an awful lot of work, which is why, one of the reasons why the Ambient Metric book is 111 pages long. Okay, so you have to exercise extreme care. So in the book, just have to yell at them. Hey! In the book, they talk about preambient metrics. And then they talk about straight preambient metrics in order to make precise what their notion of conformal invariance is. Okay, now I'm just going to have to give the bugs some treats. Here, come on, look, treats. There you go. There you go, Charlie. There we go. Right, that shut them up. We'll keep them busy for another 5 minutes. Right. So, you know, if you want to make this precise, you've got to be very, very careful, and they are very, very careful in the book. Right. Now, what about applications? Okay. So, first of all, what happens if you just run through Dirac's argument in this new setting? In other words, what happens if you just, and this works in all dimensions. You take a function of an appropriate homogeneity, which is then interpreted as a conformal density of an appropriate weight. You extend it ambiently. You look at the freedom and extension. You apply the wave operator from this ambient space. Okay. Then, and this is you know, what you're guaranteed. You know, once you've taken care of this conformal invariance and so on, you are guaranteed to get something which is conformally invariant. And what you get is exactly the conformal Laplacian. You can go through this and you can derive this formula for the conformal Laplacian. So let me just explain this a little bit more. So f is not strictly speaking a function. If you choose a metric in the conformal class, then f is a function. Okay, so a metric in the conformal class reduces everything to looking at just functions on your manifold. But what you have to bear in mind is that if you rescale your metric, then f rescales by an appropriate factor. Okay, and this weight 1 minus n over 2 is exactly the factor that you need in order for this formula to be conformally invariant. Okay, so on the right-hand side, on f is mapping to this Laplacian minus a very appropriate multiple of the scalar curvature. This expression on the right-hand side is written out with respect to a particular scale. In other words, you're choosing a metric. So for a chosen metric in your conformal class, you write down this expression involving a Laplacian constructed from that metric and the scalar curvature constructed from that metric, and just apply it as a differential operator. You find you get something which scales slightly differently, so the conformal weight changes to minus 1 minus n over 2. But the thing is that this operator very well behaves with respect to conformal changes of the metric. Okay. It also occurs in, you know, this is a famous operator because it occurs in other geometric problems, like trying to make the scalar curvature constant. So that's why it's called the Yamabe operator, but it's a well-known conformally invariant operator. And this happens in all dimensions. The other thing that happens in all dimensions is that you can look at this construction just to first order. In other words, the ambient metric construction, at least in odd dimensions, you have this power series expansion. Suppose we look at it to first order in any dimension. Then you end up with what amounts to the Cartan connection, which was as being discussed by Andy in his first talk. Okay, Molly, shh. Come here. Shh. Right, so now I should mention that the Cartan connection, which was invented in about I don't know, 1923, something like that, by Elie Cartan, was reinvented, but in a completely different way, by Tracy Yerkes Thomas in 1926, roughly speaking. And this was before, I should point out, the Cartan connection was invented by Cartan before, really principal bundles or things like that. I mean, Cartan was just, messing around with forms without explaining where they're really defined. And Thomas's construction is before vector bundles were invented. So, so you had the tangent bundle and pretty much nothing else. So these two constructions are very much ahead of their time. Shh, Molly, shh. Anyway, that's what you get out. And next time, I will explain in detail about the Cartan connection and Thomas's tractor bundle. Well, especially Thomas's tractor bundle, next time, okay? This time, however, I'll just mention what happens in a more sort of deep fashion in even dimensions. Right? So this is something you don't really see. I mean, you can try and get it from the Cartan connection and so on, but this is something which is, well, you can see that there's sort of more going on here. So in even dimensions, first of all, I mentioned that this construction breaks down in even dimensions. Okay, and the way that it breaks down in 4 dimensions gives rise to the Barker tensor. The way that it breaks down in higher dimensions gives rise to a much higher order tensor called the Fefferman-Graham obstruction tensor. Okay, and it's really quite hard to write down even what it is. You can figure out what its properties are, but to write down a formula for it is really tough. So Robin Graham, I know, has written it down in 6 dimensions, possibly in 8. I'm not quite sure, but it's something which Robin would do. If you want to look at explicit formulae, there's an article by Rod Gover and Larry Peterson, which enlists Maple to even find these tensors in higher dimensions. So you can look at the tensor in dimension 8, but it's big and it's not easy. The other thing which comes out is so-called Branson's Q curvature and these things called GJMS operators. So GJMS stands for Graham, Jenny, Mason, and Sparling. Okay, so let me just look at these things a little bit and then I'll stop. And then next time I'll come back to the Cartan connection. Okay, so actually before that, I'll just briefly mention that the last 2 chapters of this book, this Ambient Metric book, oh no, it's not the last 2 chapters, but it's anyway, two significant chapters in here are devoted, here we are, table of contents, wait a minute. Right, yeah, so chapter 7, so there's basically not a simple answer to this, to the earlier question. So chapter 7, which is actually 15 pages long, is devoted to conformally flat and conformally Einstein spaces. Okay, and the point is that even in the conformally flat case, if you try and say that the ambient metric is sort of exactly what you expect it to be by the formula that you have guessed. That was a few slides back. We guessed what might happen in conformally flat space and also when you have an Einstein metric. This guess, which apparently the whole calculations stop at second order. This is very misleading because there's the question of conformal invariance and changing coordinates and what have you. And what they show is actually there's a tensor way out beyond the obstruction tensor, which you have to control in order to control what's happening even in the conformally flat case. Anyway, Now let me mention these last 2 points, and I'll just do it in dimension 4. Okay, so in dimension 4, we've already looked at the Fefferman-Graham obstruction tensor. That's the Barker tensor. However, in dimension 4, some other very peculiar things happen in conformal geometry, first noticed by Riegert in 1984. And he wrote down something which was then generalized to, well, first of all, reinvented by Brunson and Bent Ørsted in 1991, and then Tom Brunson here in any dimension, in this little known article called The Functional Determined, wrote down something which he dubbed Q curvature, and here it is in dimension 4. All right, so here, you know, this is something you can get out of the ambient metric construction in 4 dimensions. All right, so it's a scalar invariant, but I put a dvol on the end of it because if you change your mind about the metric, at least if you rescale this metric by constants, this entire expression rescales in such a way that if you multiply it by the volume form, you get something which at least doesn't scale. It's something you can invariantly integrate, at least as a Riemannian quantity. An invariant, that's then invariant under constant rescaling. But this very, very peculiar object, you know, it's second, you know, it's nonlinear, it's second order in the curvature and so on, transforms in a really nice way if you rescale the metric. Now, it's not conformally invariant, but it rescales like this. If you change the metric by a scale, e to the 2f, so I'm taking the logarithm of the scale, calling it f, then you find that this rescales in a way which is completely astonishing. Namely, it rescales by something which is a linear differential operator applied to f. If you write down some random expression in you know, curvature, nonlinear expression like this, and you rescale the metric, the way that it rescales as a function of f is by a nonlinear expression. Involves derivatives of f, of course, but nonlinear. This one's linear. It's amazing. And because of this, you can deduce 2 things. First of all, this is conformally invariant, acting on functions. And second of all, its integral is conformally invariant as well. In fact, if you work out what its integral is, it's a multiple of the Euler characteristic, and then it's modified by the integral of the square of the Wahl curvature. This is evidently conformally invariant from this formula, but it's also conformally invariant because of the way that it scales. It rescales by p, and p is a divergence. You can just see that it is, right? So that doesn't contribute to the integral. So this, now you can get p before you get q. And historically, this is the way that it happened. So these operators p were generalized by G, J, M, and S, so GDMS operators, to any dimension and any power for which these, well, no, in dimension 4, in dimension 4, this starts with the square of the Laplacian. Okay, so look at P. It obviously, its leading term is just the square of the Laplacian applied to functions. Okay, so in dimension 6, it's the cube of the Laplacian and so on. So, okay, right. I've run out of time. So I will stop, but I will tell you more next time.
But if you want, you
then.
have 5 more minutes. So.
Well, no, this will do. Nobody ever minds if you stop early, do they? I've learned this as an audience member.
Okay, so thanks a lot for the lecture. Are there any questions?
Yeah, I have a naive question. So, why did you mention the JGMS when you were speaking about even dimensions? Because I thought
Yes, right. So they only exist in even dimensions. Okay, so if you want to get conformally invariant powers of the Laplacian, actually in odd dimensions, these you can just take any power of the Laplacian you like, and you have to modify it by appropriate curvature terms. But then when you do so, then by if you do it right, you can show that these things exist in odd dimensions, and you can either do it by the ambient metric construction, or you can do it using the Cartan connection or the tractor connection. And I'll explain how that happens next time. But in even dimensions, it's much more subtle. So for example, you'll notice that this conformally invariant powers of the Laplacian 1 existence sort of hints that there's another article. And in fact, in the same journal next door to it is the following article is called Conformally Invariant Powers of the Laplacian 2 Non-Existence. And this is by Bergman Kernel. And he shows that in 4 dimensions, you can't get a conformally invariant modification of the cube of the Laplacian. Okay, so you just take the cube of the Laplacian, you just write down all possible curvature correction terms you can imagine. You can do that by Weil's fundamental theorem of invariant theory. You can just write them all down, check how they transform, and none of them work. This has since been generalized by Rodgo and Kengo Hirachi to show that this sort of failure persists in all even dimensions. Okay, so the short answer is that these particular operators, their existence is very subtle. They're right on the boundary of this ambient metric construction. Shush! No, not you, I'm talking to the dogs.
Thank you.
Other questions?
One online. It's good to unmute.
Maybe could you read because
It's not written. I think somebody raised their hand.
Oh, okay. So online, if you have a question, please just unmute and ask.
Okay, thank you. So I have a question on relation to some graphic computations, because when you talk about Fefferman-Graham expansion and abstractions that appear there, then sort of the common physicist attitude to that is to let some logarithms in and then still solve equation, and then these logarithms they manifest themselves as conformal anomalies. So what would be the magician's attitude to that?
That's right. No. And this is exactly what happens in this particular case. Right? So this is the most naive basic attempt at an ambient metric construction. You're just looking at power series expansion. But of course, yes, you can try and put in other terms just right on the boundary where things go wrong. And a logarithm is exactly the right thing to try. And if you do that, then you get much more subtle information out. I mean, you still can't mend this process entirely, but that's correct. You try and put in a logarithm, and you get out some anomalies. So, for example, Bergman Kernel has written an article with Becchi-Rouet-Stora-Tyutin on getting these power series expansions to work with a logarithm in there, and also relating that to what do they relate it to? Scattering theory. That's what they relate it to. Yeah. So logarithm is the right thing to try, and that works to a certain extent. And in the this is a big story. And in the conformal case, in the CR case, this has been pursued very vigorously by Kengo Hirachi.
Okay.
But I've told you all I know now, roughly.
Other questions?
Is there an ambient metric interpretation of this curvature?
Oh yes, there is. Yes, that's it. In fact, that's exactly what's in Tom Branson's article entitled "The Functional Determinant." Yeah, I mean, yeah, and when so both, yeah, and when he first described it in this functional determinant, he did something which physicists would really like, namely, you just do your ambient metric construction formally, no matter what is n. Right? So n is, of course, the dimension of your underlying conformal manifold. But suppose you just take n to be a parameter, and then you look at something which is actually ill-defined when n is an even number. But nevertheless, if you just take n to be a real number and take a limit as the dimension approaches your favorite even dimension, then you can see that there's something called the Q curvature is sort of falling out. And this is how it was first determined in this article by Tom Branson, first that way. And then people didn't like this, so Charlie Fefferman and Kengo Hirachi have written an article where they avoid this, for example. Yeah, so if you want to, see a clean exposition of how you get Q curvature out of the ambient metric construction, there's an article by Fefferman and Hirachi on that.
Okay, other questions, Maxim?
Yeah, it's related to previous one, perhaps. What is why it is called Q curvature? Is it a curvature of a connection in a certain way, or it's just a name?
Oh, it's just a name. So you know, Q had not been, so it's not related to Q manifold. So Q was something that had not been used so far. So P, by the way, P is used because P stands for Panites, who wrote down this differential operator in, I think, 1983 in a preprint, something like that. So a little bit before Rigaud wrote down this operator. So P stands for Panites, and Q is the next thing in the alphabet. And Tom Branson just called it Q. Yeah, it's a Riemannian invariant which has these special properties.